Okay, so it is 2 minutes past the hour. I don't want to cut into our presenter's time anymore. So we'll kick things off with Ritu Arora at Texas Advanced Computing Center. So Ritu, take it away.
Thank you, Bob.
Oh, and sorry, one last thing before we start. If you are not presenting, good, I see everybody's doing it, please make sure that your microphone is muted. Okay, go ahead, Ritu.
Thank you, Bob. Welcome, everyone, to our presentations. Today, I'll be talking about designing reusable software that can seamlessly interoperate with other products in its ecosystem. I'll present a couple of our products as test cases, namely Grayfish and Midas. I will summarize the talk with some lessons learned in our pursuit of developing reusable and interoperable software. Now, to begin with, let me formally introduce the notions of reusability and interoperability, the two software properties that are central to this talk. So reusability refers to creating new software products using previously existing software components or other software artifacts. It saves cost and time in re-implementing or reinventing something that already exists. Functions or subroutines, for example, can be considered as the simplest form of reuse. As another example, consider the various components available through the standard template library in C++ that can enhance programmer productivity. Now, STL provides the implementation of several algorithms, containers, functions, and iterators. One can use these components across different types of application domains, and hence we can say that STL in C++ supports software reuse. Of course, the various math libraries that are supported by other compilers are also examples of reusable software. Now, talking about interoperability, I would define that as the ability of two or more software components or systems to interact with each other and exchange usable information. It is a key property that is evaluated during the process of integrating the software components from different groups or organizations to produce large software platforms. So for example, if we look at the off-the-shelf chatting software that is often integrated with online air ticket reservation systems or some of the other e-commerce systems. So these standalone chatting software is an example of an interoperable software that can work with various other large systems. So in order to be interoperable, it is important that the software components have compatible interfaces and licenses. While the interoperability property eventually helps towards the cause of software reuse, it can also lead to cost overruns during the integration step. Therefore, interoperability assessment for reusing software is critical at the time of designing tools, frameworks, and platforms using already available components in the community. So now let's think about why should scientific software developers care about reusability and interoperability? Now, for example, assume a scenario wherein you have one graduate student and an advisor working on a product, and the student graduates eventually. Now, if the software doesn't have the characteristics so that the software can be reused by others or understood by others, then it's hard to maintain the software in the long run. And likewise, like if you're working with some developers who will eventually get promoted to managerial positions, so the kind of development they were doing earlier would need to be passed on to somebody else. So for such situations, you want to have good quality software that is understandable, extensible, and can interoperate with other software components. And so these examples were just to motivate why it's important for having structurally high quality software. And interoperability and reusability are just two of the properties that ensure high quality. Now, take, for example, also the comprehensive R archive network, or CRAN, which has more than 11,000 packages that are written in R, C, C++, Fortran, and Java. These packages are developed by the user community and they provide ready-to-use implementations of specialized statistical techniques, data import and export capabilities, and have like several thousand users across the world. So they have already developed processes for developing and releasing software for the community, which I think is worth note taking. And
Ritu, let me just interrupt real quick. A few of the participants are saying that your volume is a little low. So if you can just maybe get closer to the microphone.
Is it better now?
That sounds a little bit louder now, yeah.
Okay. So should I repeat anything or are we good?
Oh, no, they said, everyone says sound quality is good, but it's just an issue of volume.
Okay, great. So the whole point I was trying to make with the previous slide was that we need to think about what happens to our homegrown software that our grad students would leave behind or developers would leave behind when they move on to future opportunities. So if a grad student and the advisor are the only two people who care about the software on the planet, then probably whatever practices they're adopting for their own internal purposes, it's good. But if you have to develop a community for the software, then it may become critical to support and maintain the software in the long run. And for doing so, it's important to have high quality structure of the software. And then I was mentioning that reusability and interoperability are two properties that can contribute to increasing the quality of your software. And I'll motivate this with example on the next few slides. And another reason like why you would want to have reusability and interoperability taken into consideration is maybe that's what your funding agency needs. So if you look at the CSSI solicitation, for example, they mention these properties as like what are the qualities they're looking for in the software at the time of funding. So also like I was mentioning, like if the software is well documented, is of high quality, then onboarding new team members in the absence of original developers becomes easy. And you never know when your software is or can be used in unforeseen circumstances. So a scientist may develop a method and a software which may end up being used in a movie, for example, in movie production. Like if you know about the movie Frozen, a Disney movie, it was and when they made for Frozen, I think they used multi-point method for simulating the snowflakes that Elsa like just creates by moving around her hands. So to simulate this, simulate these snowflakes, they used MPM or multi-particle method, which was developed in numerical computing long ago, long before the movie was made. So if you want to have bragging rights that your software can end up being used in a Disney movie, this may not be something that excites you, but maybe that could be one motivation for developing reusable and interoperable software components. Now, talking about the two case studies that I was mentioning, let me just backtrack a little bit. Like before I mentioned Grayfish and Midas, I'll mention like why Grayfish and Midas were actually developed. We were working on an interactive parallelization tool project. IPT is a high productivity tool for semi-automatically parallelizing C++ code and is mainly used for teaching parallel programming via demonstration. Now, the parallel programming paradigms supported by IPT include MPI, OpenMP, and CUDA. Now, we wanted to make IPT available to the community through a web interface because the entire tool chain on which IPT is built takes several hours to build, and it's a very tedious process. So we wanted a ready-to-use environment for our target audience, which includes domain scientists and students. So we wanted to develop a gateway for making IPT available to people and provide them a means to run the generated code by IPT on exceed systems like Stampy2 and Comet. So then we realized like whatever we are going to do for IPT, is going to be usable for our other tools like interactive tools for application level checkpointing or interactive tools for code adaptation. So all these tools have a common theme, which is interactivity, and they all can take advantage of the same gateway components that we would develop. So what we did was we generalized these requirements and developed what we now call GIB, which stands for Gateway in a Box. So Gateway in a Box provides out-of-the-box functionality for developing or supporting gateways. It provides a terminal emulator for supporting interactive tools, like features like file and folder upload, creating user accounts, LDAP integration, cloud storage, and code for compiling and running programs on Exceed systems. All of these are supported in GIB. Now, that was GIB. Now, one component that I mentioned, it was like cloud storage. I mean, that's one of the features or aspects of GIB. It provides inbuilt component for where like the results from the users, their account information, and everything else could be stored in the cloud. Now, we realized that we needed a similar functionality to like we needed for cloud storage in IPT web in our other project as well. And the other project is BOINC TACC. So basically, this is a volunteer computing project. In this project, we developed a conduit for routing high throughput computing jobs from the supercomputers at TACC to the volunteer devices by the community. When I say volunteer devices, it's not a device per se that people are volunteering, but it's the compute cycles on these devices that are donated for the project. So people can have virtual machines, or they could be owning desktops and laptops or tablets, and they attach to the project. And once they do that, then our resource pool grows and we can route certain qualified high throughput computing jobs from Stampede 2 and Lone Star 5 systems, for example, to these volunteered resources. So for this project as well, we needed a mechanism for storing the results of the jobs, but for like we needed a staging area wherein when people uploaded content from the front end, that's where it would go and be staged till the entire data is transferred and the whole file and code is zipped up and sent to the volunteer device. So we needed a staging area which is specific to user. We needed the area for like getting back the results and allowing enough time for users to download the results. So basically, in summary, we needed a way for maintaining the whole file system just like on any other supercomputing system. And we needed like ways to purge the files, and we needed ways to impose file quotas and all of these things. So we realized that the needs for cloud storage for GIB project, using which IPT web was built, and the BOINC TACC project are similar. So we extracted this feature that we built previously for IPT web and in GIB, and we named it as Grayfish. So Grayfish is a Docker container-based solution using which you can set up your cloud-based file system. And we are working on making it distributed using Docker Swarm. And basically, if you need out-of-box functionality for supporting file upload and download, admin features such as purge and scanning directories and files, you want to create user accounts, support bulk upload and download, then you might want to look at Grayfish. The source code for Grayfish is available in our GitHub repo. And just within like few days of releasing it, we already saw a lot of traction from the community. And they started integrating Grayfish in their own projects. And once they started doing that, they helped us like figuring out certain corner cases or bugs that we did not address or consider while development. They helped us improve the documentation. Some people would say, okay, these instructions are good for a Linux box, but then I'm on a Mac system and I can't use this because there are certain ways to specify like localhost and other things on Mac. So all of these input that we received from the community helped us improve the documentation and quality of Grayfish. So this in turn was fed back, or we iteratively kept improving not only the standalone version of Grayfish, but also the version that was integrated with BOINC TACC and GIP. So that was Grayfish. Other component is that I wanted to talk about is Midas. So Midas helps in converting the source code written in R, C, C++, Fortran, or Bash, or Python into Docker images. So if you want to run your code in a Docker container, but let's say if you're not conversant with how to create a Docker image, or you need a quick fix approach to do that, you could use something like Midas. So interestingly, Midas was also part of BOINC TACC. And at PERC 19, when we were talking to our esteemed colleague, Phil Blood from PSC, and he was asking about BOINC TACC, and we mentioned this feature to him, he said, well, you know what, this can be useful to other projects as well. Why don't you all just extract it and make it available as a standalone component? And in 1 week, we took his advice to heart, and in about a week, we packaged this component. We extracted it from BOINC TACC, packaged it, and made it available online as well. We're still working on improving the documentation, but basically, if you want to stand up an interface for converting source code into Docker image and push the image to Docker Hub, then Midas can be useful for that purpose as well. And IPT itself exhibits the property of software reuse. So the IPT relies on design patterns for communication and synchronization and computation. So these design patterns are existing as C++ templates and can be used in a standalone manner. So let's say IPT is good for beginners, but if you are an intermediate or advanced level user, and all you need is, let's say, a quick way to split your array and distribute it to multiple processors, and you don't want to do any of the data mapping to processors on your own, you could just rip apart the design templates from within IPT and use those as standalone components. So now one might think, why was it important to incorporate the property of reusability in IPT? Well, of course, there was the community building requirement for the project. So, I like all NSF SI² projects or the CSSI projects, we ought to have a community to sustain the project or to support it in the long run after the grant is over. And we figured that perhaps reusability and interoperability could be one way to make the software propagate. Like we can take out pieces of the software and maybe use it if it's written in a way that it can be plugged and maybe used in other places. That will, in a way, in part or whole, help in sustaining the project in the long run and in maintaining its quality if the community keeps giving us the feedback. So the lessons learned from BOINC TACC, IPT, and GIP projects is that while everything that I just mentioned sounded pleasant, it was not very easy to generalize certain features into reusable components that someone else can use, because you cannot anticipate in advance like the different scenarios that your software could be used in. So it's a time-consuming activity to work through the design meticulously. And it is hard to reuse someone else's code if there's no proper documentation, let's say, for example. Now, while we reuse works like operating systems, libraries, and middleware, I've seen, like personally, like my group, we often struggle to reuse software developed by others. And some people like myself have a mental barrier towards reuse and may feel that reuse would make you dependent on somebody else. Well, and like I figured I'm not alone. There are other people in the community who like developing things in Scratch to be in control of the software evolution and life cycle. But if there are well-maintained components in the community and packages, like the CRAN example I mentioned early on, people would use it. So So like I said, like reuse can create a dependency on something you don't own, know, or maintain, and this can be intimidating and it's understandable. And such a dependency may mean that you may no longer be in control of the entire software development lifecycle. And as a workaround for this problem, we figured that if we allow people to use our software at their own risk with enough disclaimers, and we develop the software such that each component, as long as it makes sense, we have to go to that atomic level and make that reusable, provide the interfaces which are clear and understandable, and select a license that allows others to fork from your project and make changes as needed to the code base. A thorough interoperability analysis, we figured, is also critical before integrating software components and services, especially those involving black box integration. So basically, cost-benefit analysis should also take into account any personal changes. For example, the other software that your software could interoperate with may not be maintained any further, right? And it is possible that you may not find someone who understands the tools and technologies involved in maintaining the other software or integrating your software with that component. So a thorough cost-benefit analysis is required and recommended. And then the question arises, when do you want to focus on reuse and interoperability? And when probably you can skip worrying about this? So for small-scale projects like IPT, we realized that it may not be economical to build from scratch instead of relying on integration with other products. So we did our homework and we spent a lot of time in analyzing different off-the-shelf tools, and we used as much as we could from the open source code available in the community. Now, when one needs the fine-grained ability or control to tweak the details that may affect the performance and desired output of a software, I feel it may be better to build from scratch than reuse. Especially for large-scale projects having a large community, wherein there are related objectives and there are sufficient resources, it may be better to form a technology integration and assessment team. And I feel then depending upon the recommendation of the team, one can develop reusable software components that can leverage from others' investments. In conclusion, I'll say that there is often a direct or indirect cost involved in making software reusable and interoperable, and this cost may vary from project to project. Developing well-documented and reusable software components can have a significant impact on the software quality. And before reusing or interoperating with other software, you might want to consider following things. I mean, you might want to consider evaluating the installation overheads, dependency on the project personnel and changes, software maintainability in the long run, the change management process, and the existence of shared documents about interoperable software units with high-level architecture details. With that, I would like to thank the National Science Foundation for generously funding the IPT and BOINC TACC projects. And thanks to the audience for listening to me. And I'm ready to field questions if you have any.
Great, thank you, Ritu. So do we have any questions for our speaker? Okay, if not, I just have a few questions, comments. No, actually, I see something coming through the chat. No, just a thank you. So Ritu, first of all, I was thrilled to hear that a piece of scientific software was used in Frozen.
Yeah.
That was a very unexpected reuse, and I'm sure that 4 to 7-year-old girls across the world are really excited about HPC now.
Yeah.
But my question I have here is, what was your presentation? Was this essentially presented at PERC 19?
No, at PERC 19, we mostly covered Grayfish.
Oh, okay. All right. Yeah, just because if you had, I would, it'd be good to refer. refer folks to that paper. Do we have any other questions for Ritu? I'm sorry, I just saw the comment here from Vanessa Sochet. Actually, my boyfriend is incredibly fond of this movie. But I have to be honest. I've never seen it. Yeah. But I've heard it's very good.
Yeah, it is, and it's highly recommended. Just to see the marvel of like simulation, like how they simulated Elsa's clothes, like when she moves, how the clothes move. It's a hard, like simulating diaphanous material is a hard problem, and they did it pretty well in that movie. And multi-point method that I mentioned, it's a numerical computing method developed several years ago that they used for simulating like how the snow will flow in different directions or move in different directions. So that was very interesting when I learned about this.
Great. Do we have any other questions or comments? All right, well, we are just going to wait until 10:30 to have our second speaker present, just in case there are folks who were planning on joining just for the second half. While we're waiting, I just want to mention in November we do not have an ECSS symposium. We always skip November because of the conflict with SC, but we'll be back again in December.
I had a quick comment. Yeah, I enjoyed your presentation, Ritu. I had one question about when you have a dependency to a library, how do you feel, about a continuing acceptance of that, if it's not some standard library, but something somebody wrote, versus sort of maintaining your own copy of it? We've gone through a lot of these types of discussions in the GenApp project, and because we want to maintain maximum availability of the running gateways, as to how much do we allow other people to have versus what we're using.
It's a very tough situation that we were in as well, and just to elaborate on that, we were using a version of ROSE compiler developed from Lawrence Livermore National Lab. So the whole IPT software sits on top of a source-to-source compiler from Lawrence Livermore National Lab, and this is called ROSE. And ROSE in turn has dependencies on certain versions of GCC, certain versions of Boost libraries. And the whole tool chain has such rigid dependencies, it's hard to evolve the software without breaking anything. And there are times when we thought, oh gosh, I mean, the only way to probably beat this problem is like if we start writing our own compiler, like especially a compiler like ROSE. I mean, of course, that's not feasible in the amount of time and resources we have, but we have been at a point like of aggravation with the changes in software that are software dependent on, that we felt like, I don't know if frustrated is the right word or how to say that best, but yeah, we felt that we hope we had more control over all these things.
Yeah, that's well said. Thank you.
Thank you.
Sorry, thank you, Emery, for the comment there. And we're gonna move on to our second presenter. So Marty. So Marty, are you ready?
Yeah, let me just get this in full screen here. Okay, yeah, I think I'm ready. All
right, take it away.
Great. Thanks everyone for coming out and listening to the talks today. This talk here is actually on an exceed proposal me and my PhD advisor wrote a couple years ago, growing out of a project as part of my dissertation. So Bob sort of asked if I had something to present. We're still sort of working on this here and there. So I thought I'd give you a quick overview of this problem and what we've been doing. So the title is Exploring the Dynamics of a Quantum Mechanical Compton Generator. And so I'll try to explain all the terminology that goes into sort of understanding the problem, give you a sense of what the computational challenges are to doing these simulations. And at the end, I have some cool visualizations we got out of the exceed allocation that I'll try to explain. So just some overview of the problem. This is actually a problem we just randomly saw in a classical mechanics textbook a while ago, and we were sort of wondering whether or not we could sort of simulate a quantum mechanical version of this experiment that was done by Arthur Compton back in 1913. So the experiment essentially starts with a tabletop size of experiment that's able to actually measure the rotation rate of the Earth independent of any astronomical observation. This is sort of what the devices looked like that Compton created. Essentially, it consisted of a large ring of glass tubing filled with water and oil droplets. Essentially, the ring was roughly about half a meter across, if I remember, maybe a centimeter and a half in thickness. And essentially, what happened was when you rotate this ring around an axis passing through it, depending on where you are on the surface of the Earth, after a complete 180 degree rotation around this axis, the oil and water droplets in the tube will begin to rotate, and they'll acquire this drift velocity. And this drift velocity is actually related to the radius of the ring itself, the rotation rate of the Earth, and the latitude that you are located on the Earth. Now, this is pretty interesting, right? I mean, there was up until this, I mean, this type of experiment, there's only so many types of experiments you can think of that actually will, give you a sense that the independent of any astronomical observation, how do you know that you're on a rotating Earth, right? So if this is kind of like a cool little textbook experiment that you can write down the equations. It's a couple pages to derive this drift velocity, and so we were kind of curious, like, well, can we do this with a quantum Compton generator? Essentially, when we're doing quantum mechanical experiments or simulations, the fundamental motivation usually at the start is, if you did this a similar experiment in a quantum mechanical system, at some limit, the average, in this case, drift velocity you would see in the quantum system should correspond to the classical velocity observed in the large scale experiments. And so if you actually write down some sort of back of the envelope type calculations, if you assume sort of if you wanted to excite one angular momentum unit, unit of angular momentum in the system, sort of take a mass of an atom in some of the experiments that they do today, and take the rotation rate of the Earth, plug it in sort of a mid-latitude, you get the radius of the ring in this quantum mechanical system needs to be on the order of a few hundred microns or something like that, which is actually the scale at which some experiments today are done with sort of macroscopic quantum mechanical gases, essentially called Bose-Einstein condensates. And so this was not really out of the realm of possibilities of an experiment you might be able to do one day. There's sort of complicating factors with the strength of gravity in these systems, but we just kind of wanted to see, can we simulate this, check that it agrees with the classical system, and see if there's any other sort of interesting dynamics in the system that we might want to study. So just to back up for a second, the thing that's one of the difficult parts of this simulation is that we're dealing with rotating reference frames. Okay, so we're going to simulate these quantum mechanical ring-like structures in a rotating reference frame, and so this is gives rise to what we call inertial forces. So just the general definition of inertial force is essentially it's an apparent force that exists in these non-inertial reference frames. So anything that's sort of an accelerating reference frame. This is a good example here that shows sort of in an inertial reference frame, basically when you're at rest observing an experiment. Here in this case, we have a pendulum in a train car that's accelerating towards the observer, the inertial observer at the top of the screen. And basically the person standing outside the car sees that there's a tension in the string, there's gravity pulling down on the pendulum bob, and the train is accelerating to the right here. And they can sum up all the forces in this system. So this is your Newton's second law, F equals ma. All the forces acting on the system should add up to the acceleration that's observed. If you take an observer and actually put them in this accelerating reference frame, this non-inertial reference frame, the observer is actually accelerating with the pendulum in the train car. And so in this case, it actually appears to them that there's this so-called inertial force or fictitious force that's also pulling back the bob in the train, that's keeping it stuck in this sort of at this angle here. And so when we simulate quantum mechanical systems, we're also going to get a set of inertial forces acting on the system. Okay. So in rotating reference frame, there's a few different types of inertial forces we'll see. And so the one that most everybody is probably familiar with is what we call the centrifugal force. This is sort of if you're driving in your car and you take the off-ramp or on-ramp onto the to the highway and there's a nice big curve. This is what the force that you sort of feel like you're being thrown against the side of the car towards the door or in one direction or the other. So as you go around the bend, you feel like you're being thrown outwards. Or if you're on a merry-go-round, you feel like you're being thrown outward as at a certain speed or a certain acceleration. Less familiar, but you sort of generally colloquially understand that there's hurricanes will rotate one way in the northern hemisphere versus the southern hemisphere, or the toilet bowl go one way in the northern hemisphere versus the other. This is sort of where that comes from. This is the Coriolis force. So it's sort of a force that is deflected depending on the rotation of the system and the velocity of the particles in the system. And a little less familiar for most people is this Euler force. This is related to changes in the actual rotation rate of the system with time. So how the angular velocity or angular acceleration is changing. And this is kind of if you're on a merry-go-round and as the merry-go-round starts picking up speed, this is the force that you feel kind of thrown backwards as it starts spinning up, or as it starts spinning down to stop the ride, you sort of feel like you're being thrown forward a little bit as you're on the horse. So these are the three forces that are observed in rotating reference frames. So just a general motivation for what's interesting about doing these sort of quantum mechanical simulations and these non-inertial reference frames. It goes back to a very old problem called the bucket problem. This is Newton's bucket problem. Essentially, in this, his thought experiment here was looking at if you take a bucket of water and you begin rotating it, eventually the surface of the water, as the bucket rotates, the water will eventually, through friction and things, start rotating with the bucket itself. And eventually, if you rotate the bucket, right, you get kind of this parabolic shape to the surface of the water. However, if you stop the rotation of the bucket, the water actually continues to rotate, and you see still this curved surface, even though the bucket is no longer rotating. And so the fundamental question Newton asked is, okay, if you see this curved surface of the water, you know that the water is rotating, but what is it rotating relative to? And so this is sort of a fundamental question that doesn't have a complete answer, I would say, yet. I mean, essentially it has to do with how we interpret inertia in the systems and what is sort of the source of inertia in physical systems. And so there's sort of a long philosophical discussion you can have on this, but this is sort of the intersection of, if you start doing these types of equivalent experiments in quantum mechanical systems, maybe we'll see some interesting behaviors, sort of my general motivation for the interest in sort of looking at quantum systems in rotating reference frames. Now, if you're not familiar with quantum mechanics, this is the Schrodinger equation. This is essentially our Newton's second law, F equals ma, for in a quantum mechanical system. There's, to describe the particles in the system, essentially there's this notion, this object called the wave function that describes essentially where the probability of finding quantum mechanical particles are in the system. So this Schrodinger equation determines how this complex valued wave function evolves in time. And in the simplest case here, we see that there's also a term in the system that has to do with the kinetic energy of the particles in the system, and one with the potential energy of the system, if there's any external fields or forces acting on the particle through this potential term. And although the wave function is a complex value, the probability density, sort of the mod squared of this wave function, really does represent where we, if you ever, where we would expect to find the quantum mechanical system located at a particular point in space and time. And so this sort of, the integral over the mod squared of this wave function will be, should be 1 at all times. Now, just like in Newton's second law, when you go into an inertial, non-inertial frame, such as a rotating reference frame, there's additional terms that come in. So this additional term here in the center is this minus omega dot L. So this is the angular velocity vector that comes with that defines the magnitude orientation of the reference frame that's rotating with respect to a fixed inertial frame. And here, the Coriolis force, the centrifugal force, the Euler force, they're all coupled together in this one term that is coupling the angular velocity of the rotating reference frame to the angular momentum, actually, of the particles in the system. So this is where these forces actually come about in the Schrodinger equation. Now, like the bucket problem, there in quantum mechanical systems, there's a little bit different, there's more restricted motion that's allowed than, say, a classical fluid like water. And so this is actually an experimental picture of what we call quantized vortices. These are sort of like little tornadoes, quantum tornadoes, essentially, that carry the angular momentum in the system. And this is actually one part of the simulations that's a bit computationally challenging. So if we're going to simulate this large scale sort of ring-like structure, there's also going to be likely embedded within it very small scale structures like these quantized vortices, because essentially these quantized vortices are what should be carrying angular momentum into the system as the simulation goes about. So one of the computationally challenging parts of this problem is you have large scale structure and small scale structure at the same time that you need to resolve across the system. There was a custom code that we developed for this. Actually, I mean, this problem here was really the test case of like how far could we push the code, or like how difficult might some of these simulations be. And so this is the code that was written for it. It's written in Fortran. It's about 5,000 lines of code. To solve the Schrodinger equation in a rotating reference frame, we actually used a general RungeKutta fourth order algorithm with central differencing. It's a hybrid MPI OpenMP code. This is sort of our first code where we actually wrote MPI-based code. So we use sort of just a simple 1D domain decomposition on a regular 3D grid for the simulations. There's different modes of I/O that it can use. It's sort of, you can do limited I/O where you only sort of output sort of average values, what we call expectation values from the quantum mechanical system we might be interested. As part of the succeed allocation, we actually implemented some parallel I/O with VTK formatted output for the wave functions, and also some MPI-IO output as well, binary output. So I think I might just, in the interest of time, skip over some of these details. If you're interested, those will be in the slides, just sort of the method. So there's this generalized RungeKutta method that was implemented, sort of allows you to tune between sort of the classical RungeKutta that you know about and others to sort of put different weights on the different steps here. It was central differencing. We implemented both second order and fourth order, but most of the simulations all used second order finite differencing. Again, it was a 1D slab sort of domain decomposition. So essentially all of the halo exchanges for the finite difference method were just on the boundaries along the z-axis in the system. Sort of what the MPI communication pattern looked like, sort of used a even odd 2-round sort of MPI communication pattern for each time step. So essentially the first step is, the even, upper boundary is sent to the lower bound of the next MPI process and vice versa, back and forth. So it's pretty straightforward, I think. As part of preparing for the exceed allocation proposal, we did some strong parallel scalability testing on Comet. So this is varying sort of the number of MPI and OpenMP processes. In general, we found at the end, at least on Comet, the OpenMP wasn't really helping much. So actually, as we just went, so when we did the simulations, we actually went to all MPI processes. But here with a hybridization of like 4 MPI processes per and 6 OpenMP processes per MPI process, OpenMP threads per MPI process, we got up to about 300 speed up on a little under 1,200 cores on Comet. So it wasn't great efficiency. But it was enough to do the job, essentially, for the simulations. There was some weak scalability testing at one point, but not a lot done there. In addition to sort of parallel scalability testing, we did some verification of sort of the order of accuracy for the implementation, both temporal and spatial. Everything was in line when we did it. We also did some verification of solutions. So we sort of had some analytical solutions that we could check against the numerical solutions, and everything lined up quite well. Okay, and so just to come back to, so that's sort of a general overview of the code and sort of the testing we did. So what I really want to do in the last couple of minutes is kind of show you some of the simulations that came out of the process, because they were pretty interesting. So one of them, so this is again the sort of initial state we'll start with. We essentially have a quantum mechanical ring here. So this is actually showing the density of the where the quantum mechanical particle in the simulation might be located. So this is sort of we have a ring-like structure. It's a simple harmonic oscillator ring. So this is the potential that's sort of that quantum mechanical particle is sitting in. So it's sort of starting at rest in this sort of Mexican hat-like potential. And so one of the things that we did to sort of minimize the computational effort needed here was actually instead of rotating the ring itself, instead of rotating this potential end over end like you would sort of imagine you might try to do naively, we actually actively transformed the angular velocity vector in the system. So instead of rotating the potential end over end, we actually rotated the reference frame around in this system. And so what that allows us to do, instead of having this ring sweep out a large volume, the volume in the simulation could stay fixed, and so save on sort of the computational effort needed to model the entire system. So just by actively transforming this rotating reference frame, we were able to keep the computational cost lower. Okay, so these are sort of what we had prior to the preliminary results we had prior to the exceed allocation. Essentially, during my dissertation, we had very limited storage space, so we couldn't actually output entire wave functions and actually look at what was going on in the system. So all we had to go on was looking at the overall average angular momentum in the system, essentially, right? If this ring starts rotating after the flip, after this Compton flip, you should see some pickup in the angular momentum around the z-axis. And so this is a simulation that shows sort of, you see this bump in the middle, that's sort of where the flip is happening. But before and after the simulation, before and after the flip, there's actually no change in the angular momentum in the z-axis. However, if you speed up the rotation rate of the system, we actually see before the flip and after, here before the flip, at around sort of 10 oscillating units this time here, we see the flip happen, and after the flip you get this non-zero angular momentum around the z-axis. So something here is definitely rotating after the flip, and so this is like sort of the first sign we had that, okay, yes, this is working. You can also start with a non-zero angular momentum like we did in this simulation, and again we see an overall net change in the angular momentum before from before the flip to after the flip. And so this is essentially all we had to go on, and before the exceed allocation. And so what we, the one thing that was interesting though is the numbers here in the expected change in the angular momentum didn't add up to what we were seeing, what we could sort of do on the back of the envelope calculation from the classical experiment. And so what we decided we really need to do was actually just get full visualizations of these wave functions and see what's actually happening to sort of get a better idea of what's going on in the system to sort of carry this analysis forward. And so this is sort of some preliminary results. So this was the first visualization we had. This was sort of a 2D sort of integrated density profile. And if you remember a little bit earlier in the talk, there was this I mentioned these quantized vortices will be sort of these little tornadoes of angular momentum that should be apparent in the system. And so this was the first hint we had going into the allocation that we definitely should be seeing vortices in the system. We just need to sort of understand what's going on a little bit better. And so this is the exceed allocation, and let me just skip ahead here since we're running out of time with some of the visualizations here. So hopefully these pop up. So this is the equivalent to sort of that 2D visualization that I showed just a slide or two ago. Oops. Sorry about that. Let me go ahead and so let me start this over here. Okay, so here we're looking at a side view of the Compton generator. So this is sort of looking at the density of the wave function from the side. And as you kind of can see that in this case, after the flip, there's a lot of transverse in the oscillations in the z direction. So it's a bit crazy what, let me see. Sorry. Oops. Oh, there we go. So this is looking down the axis of the same simulation. So you can kind of see these circular structures that are probably vortices in the system that are coming about. Let me just skip ahead here to a few more. So this is sort of the best simulation we had, where essentially what we did in this case is we really compressed the z-axis of the trapping potential to quiet those transverse oscillations in z. And so this is the density of the wave function again. So after the flip, you see sort of these structures form. You see these little circular holes in the density here. Those are the vortices coming into the system. And you obviously see that there is a drift velocity after the flip here, right? So you start at rest, the reference frame is rotating around, and then after you get this drift velocity with a lot of complicated dynamics in the system. And this is a little bit more complicated visualization that we had. Essentially what we're looking at here again is the density of the wave function, the probability density. On the right is sort of a measure of the velocity in the system, and the left is a phase. So around these quantum vortices, you'll have this 2 pi phase winding that we should see to confirm that they're quantized vortices in the system, essentially. Oops. Sorry, I think my visualization got stuck or something here. Anyway, let me go ahead and try to get out of this. But I know we're running a load on time, so while this works itself out, let me go ahead and stop here and take any questions that you all might have.
Hey, thank you, Marty. So do we have any questions for our speaker?
Yeah, this is Sergio. You know, by the equivalence principle, inertial forces are another way of saying gravity. So are there any implications here for quantum gravity?
Yeah, so I mean, that's sort of an interesting question, right? So if you go back to sort of, as I mentioned, the Newton's bucket problem, I mean, the interesting thing there is, right, there's, if you've ever heard of Mach's principle, and sort of this was essentially his interpretation of the bucket problem was the reason the water's surface is, as the water is rotating, the surface is still curved, you sort of have the centrifugal force is still there. It's not related to the bucket at all. It's actually because the water is rotating relative to the rest of the mass distributed in the universe, right? So this is sort of was some inspiration for Einstein and general relativity. And even in general relativity, Einstein showed that if you have a mass that's rotating around a pendulum, it affects the motion of the pendulum through something that looks kind of like an inertial force, essentially. The thing there, it doesn't quite exactly solve the entire problem. There was another physicist later, after Einstein came up with general relativity, that showed that you can actually have a universe that's rotating in general relativity, but what would that universe be rotating relative to? It's a little strange. So in general, I mean, if you can explain, you know, inertia and rotation and things like that, I mean, yeah, there's open problems, I would say, is kind of where I would put it. So looking at sort of just classical quantum systems like this in rotating reference frames, you know, maybe if actually do an experiment here, you'll see some deviations. It's kind of hard to say, but if you don't sort of understand sort of what the Schrodinger equation predicts first, you know, you can't. It's you need to know that a little bit before you do the experiment, I guess, is what I would say.
All right, thank you.
Yeah,
And we have another question from Brian Rainey. So do you want to go ahead and ask?
Oh, okay. Yeah, I see it here. What was the difference in resolution between your tests and the simulations you ran with the exceed allocation? Yeah, that's a good question. I think I'd have to go back and double check for sure, but I did put a slide here that shows roughly what the number of points essentially are in the 3D grid here. So if the largest simulations were 1152 by 576. So that's the total number of points represented that represented the wave functions in the largest simulations. That's probably, I think, double what we were able to do before on sort of the campus clusters we were using during my dissertation. work. And just to give you a rough scale of what that actually translates to, so this is for that size simulation, compressed the wave function, all of the data for these simulations was about, for one simulation was about 3.4 terabytes, right? So for this simulation here, shown on the screen, this is, took probably 6 or 7 terabytes uncompressed of data. So it's this is one of the main limitations sort of to the allocation we had, where essentially we had about 13 terabytes allocated on Comet Data Oasis to store the wave functions. But we did all the visualizations on Maverick, and so we had to ship the data over like sort of chunks at a time, about 40 frames at a time, to fit it in the scratch space that was available there. So it was sort of a bit of a hassle wrangling data back and forth and running the visualizations, which were all done with Visit, actually, or sorry, Paraview. So yeah.
Great. So we are about 3 minutes past the hour. Do we have any more questions?
Can you hear me, Adi?
Yeah.
Yeah.
So it looks like these vortices are actually, coming off, and essentially the whole system is getting kind of destroyed here, at least from this visualization. I mean, does it happen like that? So is there a, what is called, the system becoming, is it unstable because of some parameters, or, actually the system actually gets destroyed through this rotation?
No.
Or there is some relativity, that we're not considering.
Yeah, no. The system is not being destroyed here. It's more of the the vortices entering the system here are what are sort of contributing to the total angular momentum in the system. So yeah, there's definitely obviously you see the vortex structures sort of entering from infinity, essentially, is sort of what you would expect, right? So right near the boundaries, right, there's no density in this, there's very little density in the system. So here in the visualization, you see on the left side, there's this sort of these phase structures that are coming in sort of from infinity towards the center of the system, and then as they pass through the density, those are where the vortices appear in the density, in the probability density. And so it's not that it's being destroyed. I mean, it's a big mess here. It's hard to understand if you haven't looked at this stuff a lot before. But yeah, no, it's not unstable in any way. It's just a matter of, this is sort of one of the.
So these things that are coming off, these vortices are not just going away; they're just staying there and rotating.
Yeah, I mean it's complicated. I mean we haven't done like a full exploration of these data sets, right? I mean we have the full 3-dimensional wave function here, so it'd be cool to like fly in and see a little bit better what's happening around these structures to understand things. I mean, what we're hoping in sort of the future work is, right, we might be able to quiet down some of these dynamics that we're seeing in this case with compressing the ring in the radial direction, right? So we definitely reduced excitations in the z direction, so in the vertical direction here with some of these simulations, but we haven't really looked at sort of compressing in the radial direction, which might sort of get the system into a more easy to manage or easy to understand sort of regime is what we're hoping. So
this is a time dependent Schrodinger equation that you solved, or time independent?
Time dependent, yeah. So this is the simulation going over time, right? So we start off, the blue here is the density at the start, and then we flip the ring, and sorry, it's a lot of delay here or something, but.
Okay, thanks.
Yeah.
Can I follow up on that question? So ultimately, as time goes on, will the vortex kind of stop and return to the initial sort of configuration, or did they just kind of continue indefinitely on their own?
They should. Since there's now angular momentum in the system, there's always going to be some vortices around. Like how these things evolve over time in the system is, I don't think it's. We don't have a good model to sort of necessarily predict exactly what the configuration should look like. We mentioned, someone mentioned earlier, stability in the system. There's actually the code here actually solves a nonlinear version of the Schrodinger equation as well, which supports vortices as well. And in this nonlinear case, you can actually show that sort of you can write all of these vortices are what we would call charge one vortices, most likely, where essentially it's a single unit of angular momentum in them. Essentially, you can show mathematically that anything above charge one is unstable in the nonlinear system. And so this is sort of one aspect of what we know will be happening with the vortices. But yeah, all this complicated dynamics that we see here, it's sort of something to be understood, I guess.
And one last question about your workflow. You mentioned that you did all this calculation on Comet, then you generated each individual JPEG image in this frame and then transported over to Maverick to create the actual movie using Visit. Is that correct?
So it was a ParaView we used, but no, actually, we actually transferred the raw data to Maverick and ran the visualization workflow on Maverick there. So on the raw data. So everything visualization wise was generated from ParaView on Maverick.
Okay.
So that was sort of the one of the bottlenecks where we didn't quite have enough storage space to keep everything around. So we had to, as quickly as we can do the simulations on Comet, we had to ship it over to Maverick and run the visualization as fast as possible so we could do a different simulation on Comet without losing the data, essentially.
Okay, thank you.
Great. Thank you, to both of our speakers and for all of the excellent questions. So we will wrap up now. Again, thank you, Ritu. Thank you, Marty, and hope to see all of you in December.
Great. Thank you.
Thanks, Bob.